Welcome back to my channel. In this video, we are exploring how to measure sentence similarity using a controlled swap test, a beautiful fusion of natural language processing and quantum computing. Before the quantum magic happens, we begin with a simple but essential workflow. First, we take a reference sentence and one or more query sentences, and convert each of them into numerical vectors using a classical NLP technique called CountVectorizer. This gives us a fixed representation of each sentence based on the words it contains. Once we have these vectors, we normalize them so they can be meaningfully compared. The next step is to translate these classical vectors into the quantum domain. We do this through angle encoding, where each element of the normalized vector becomes a rotation on a corresponding qubit. By applying these rotations, we transform each sentence into a quantum state, a structured, amplitude-based representation that the quantum computer can process. With both sentences encoded as quantum states, we can now apply the controlled swap test. This elegant quantum routine uses a single ancilla qubit to interfere the two states and extract how similar they are. The quantum computer essentially asks, how much do these two states overlap? And that overlap, captured through the probability of measuring the ancilla in a specific state, directly reflects how similar the original sentences are. In this way, classical language data flows through a quantum pipeline, letting us tap into quantum interference to measure semantic similarity. Before we dive into quantum circuits, we first need to turn our sentences into something a computer, or in our case, a quantum computer, can understand. And the first step is vectorization. On your screen, you can see the Python snippet where we start with a small corpus of sentences. Quantum computing is amazing. Classical computers are still useful. Quantum and classical computing can work together. We use CountVectorizer, a simple but powerful tool from scikit-learn, to convert each sentence into a numerical vector. CountVectorizer scans through all the sentences, builds a vocabulary of unique words, and then represents every sentence as a vector based on how many times each word appears. Once the vectorizer fits on our corpus, it prints the vocabulary and the corresponding vectors. This is important. The vocabulary defines the feature space. If we change the vocabulary later, our comparison becomes meaningless. So when we introduce a new query sentence, quantum computing is very good. We transform it using the same vectorizer, ensuring all vectors stay aligned in the same semantic space. The result: a clean, numerical representation of both the reference and the query sentences, ready for normalization and quantum encoding. This classical preprocessing step is what makes the quantum part work. Vectorizing is like preparing the ingredients before cooking. Once everything is chopped, cleaned, and measured, the quantum kitchen can do its magic. In the next part, we'll normalize these vectors and encode them into quantum states, continuing our journey toward the controlled swap test. Alright, now that we've transformed our sentences into numerical vectors, it's time to cross the boundary from classical computing into the quantum world. And to do that, we use a technique called angle encoding. On the screen, you can see a function named angle_encode_vector. This function takes three things: a quantum circuit, a set of qubits, a real-valued vector, and its job is simple but profound. Turn that classical vector into a quantum state. Here's how it works. First, we normalize the vector. Why? Because quantum states must be normalized. It's a fundamental rule of quantum mechanics. If the vector is 0, we throw a warning because you simply cannot encode a zero magnitude vector as a quantum state. Next, each value of the vector is mapped to a rotation angle using the formula. Theta is equal to 2 asterisk arcsin value. Then we apply our y rotations, one rotation per dimension of the vector. Each qubit receives one component of the sentence vector. This is the moment where language enters the quantum world. Think about it. The structure of the sentence, the frequency of each word, the meaning captured in the vector. All of that becomes amplitudes of a quantum state through these carefully calculated rotations. Angle encoding is efficient. It's hardware friendly. And it transforms something symbolic, like the sentence, quantum computing is very good, into something physical. A quantum state that can interfere, entangle, and participate in a swap test. This encoding step is crucial because the swap test doesn't work on raw text or numbers. It only works on quantum states. So this function is our bridge between classical NLP and quantum similarity measurement. In the next segment, we'll build the controlled swap test circuit that compares to encoded sentence states and tells us how similar they are. Now that our sentences are fully encoded as quantum states, it's time for the heart of this entire experiment: the controlled swap test. On screen, you'll see the quantum circuit being assembled step by step. We start by creating a quantum circuit with enough qubits to store the ancilla qubit, which controls the test, the qubits for vector 1, the qubits for vector 2. These two vectors come from our sentences, the reference sentence and the query sentence. Step 1. Encoding the sentences. We call angle underscore encode underscore vector wise. This loads each sentence into its own quantum register. By this point, both sentences exist as quantum states, ready to be compared. Step 2. Begin the swap test, the first Hadamard. We apply a Hadamard gate to the ancilla, QC.H0. This puts the ancilla into a superposition, allowing the circuit to compare both sentence states in parallel. This is where quantum advantage begins to spark. One qubit influences the interaction of entire vector states. Step 3. The controlled swap operations. For each dimension of our encoded vectors, we apply QC.CSWAP0, V1 underscore qubits I, V2 underscore qubits I. These are Friedkin gates, or controlled swaps. If the ancilla is in state gate 1, the corresponding qubits of the two sentence states are swapped. If the ancilla is gate 0, nothing happens. This interference process is what allows the circuit to detect how similar the two states are. If the sentences are similar implies the states don't change much, implies the ancilla's measurement stays close to 0. If the sentences differ implies the states interfere destructively, implies the ancilla is more likely to flip to 1. Step 4. Close the test, second Hadamard. After all controlled swaps, we apply another Hadamard. This completes the quantum interference pattern that encodes similarity. Step 5. Measure the ancilla. Finally, we measure only the ancilla qubit. This single measurement gives us the key probability value used to compute. Sentence similarity is equal to 1 minus 2 multiply probability of ancilla is equal to 1. And just like that, the quantum circuit tells us how similar the two sentences are. Alright, now that we've built and executed our controlled swap test circuit, the quantum simulator gives us something very simple: measurement counts of the ancilla qubit. But what does this mean? And how do we turn this into a similarity score between two sentences? That's exactly what this next function does. Definite swap underscore test underscore similarity underscore from underscore counts. Step 1. Count the total shots. Shots is equal to sum of counts dot values. Each shot is one run of the quantum circuit. More shots mean more reliable statistics. If there are 0 shots, we throw an error. You can't compute probabilities from nothing. Step 2. Compute the probability of measuring 0. We only care about the rightmost bit, the ancilla's measured value. Every time the ancilla is measured as 0, we add it to p0 underscore counts. This gives us the probability of measuring the ancilla in the Kate 0 state. Step 3. Convert p0 into similarity. Here's the magic formula from quantum theory. Similarity is equal to multiply probability of 0 minus 1. Why this works? The swap test encodes the square of the inner product between the two quantum states in the probability of measuring 0. Similar sentences means quantum states look alike means probability of 0 is high. Very different sentences means states differ means probability of 0 drops. So a similarity of 1.0 means the sentences are nearly identical, while 0.0 means they are very different. Step 4. Clip for numerical stability. Because simulators and floating point arithmetic can introduce tiny errors, we gently clip the result into the valid range. Finally, this function returns two values. P0 means the raw quantum probability. Similarity means the meaningful similarity score. This is where our entire quantum pipeline comes together. From text to vectors to quantum states to interference, and finally to a real similarity number we can compare. We've reached the final and most exciting part of this journey. Executing the swap test circuit and turning its results into a ranked list of sentence similarities. Let's walk through what's happening in this last block of code. Step 1. Running the circuit on a quantum simulator. Here, we are using Qiskit's A simulator, which emulates a real quantum device. We transpile the circuit so it matches the simulator's gate set. We run it 500 times, or shots. This gives us reliable measurement statistics. The job returns a result dictionary with counts for the ancilla bit. This tells us how many times the ancilla ended as 0 or 1. Step 2. Converting counts into similarity. We use our earlier function to convert raw measurement data to probability P0. Probability P0 to sentence similarity score. This is where the controlled swap test finally pays off. Step 3. Storing the results. We sort by similarity in descending order. Highest similarity means closest meaning. Lowest similarity means least related. This gives us a quantum-powered semantic ranking. And just like that, we've built a full pipeline. Text preprocessing, vectorization, quantum angle encoding, controlled swap test, quantum measurement, sentence similarity ranking. This is a practical example of how quantum computing can enhance semantic search and NLP tasks even with small circuits and basic encodings. And that brings us to the end of our journey into quantum-powered sentence similarity using the controlled swap test. We started with something simple, just a few sentences. But step by step, we transformed those sentences into vectors, encoded them into quantum states, and compared them using one of the most elegant quantum algorithms ever designed. What makes the swap test so powerful is its simplicity. With just one ancilla qubit and a handful of controlled swaps, a quantum computer can capture the inner product between two high-dimensional states. In our case, those states represented the meaning of sentences. This means that quantum devices aren't just number crunchers. They can genuinely participate in language understanding tasks. Even on simulators, we see how quantum interference patterns reveal semantic closeness. Which sentences share concepts? Which ones differ? And how strongly they relate. And the best part, this is only the beginning. As quantum hardware improves, as encoding schemes become richer, as quantum NLP models evolve, we'll be able to measure meaning, context, and emotion with levels of nuance classical models struggle to reach. So whether you're a quantum enthusiast, an NLP researcher, or someone just curious about the future of computing, you've now seen a glimpse of how quantum algorithms can shape the next generation of language technology. If you found this useful, leave a comment, share your thoughts, and stay tuned. Because in the world of quantum computing, every simple circuit opens the door to something extraordinary. Thank you for watching. And I'll see you in the next video.